Welcome to our last section of Chapter 9, Conditional Probability and Bayes Formula. So this is going to talk about what happens when I have events that are based on something that happened prior to it and so forth, and general Bayesian statistics. We're going to get to just the tip of this iceberg. So let's start with conditional probability. It says this: if let A and B be a sum source sample space, then the conditional probability of B given A denoted B bar A. So this literally means that A has already occurred. What's the probability of B? So A is true. Then what's the probability of B? That's going to be the probability of A intersect B. So probability they're both true, and divided by the probability of A. So let's look at this in an actual example so you understand what I mean by all this. So I have two fair dice. One is blue and the other gray. So they're clearly separate. What's probably the sum of numbers showing face up is 8, given that both numbers are even. Okay, so we have a problem. We have something that are already even. Both numbers are even. So in our totals, so to break this down, we have 36 possible options because each dice has 6 options. AB is the outcome of what we're going to call this. AB is that outcome where the blue dice is A and the gray dice is B. So let's look at first A be the possibility that both numbers are even, and B be the event that both numbers are odd. So both numbers are 8. Sum is 8. So these are all the possible combinations up here. 2, 2. They both are 2s, 2, 4, 2, 6. So notice on the first one, the blue dice are all 2s, and the blue dice are all 4s, and blue dice are all 6s. And you can clearly see that there are 9 possible options for that. Now, however, the sums that add up to are 2 and 6, 3 and 5, 4, 4, 5, 3, and 6, 6. Where these intersect, you can clearly see is 2, 6, 4, 4, and 6, 2. So the probability that you roll a B, knowing that they're already even, is going to be this kind of idea. Now, this is one that, how do you find that intersection? Well, you can still do it the same similar sort of way. Anyways, there's a lot of different strategies we can talk about here. So, but this one, because the first dice, really what this is, the first dice had to be a 2, then what are the possible 2, 4, or 6, and each one has only one way to solve. That's actually how you could have come with that 3, even if you didn't brute force it. But this probability then is going to be 3 over 36 over 9 over 36, 3/9 or 1/3. So there's a 1/3 probability that this actually will occur. So if I roll the dice and you tell me they're even, and I have to guess, do they add up to 7? Well, if they're even, then 1/3 of those are going to add up to 8. And the way to look at that is, let's just look at this situation. Another way to think about it is, look at this situation. This is what I'm saying. So I already know you're telling me that I'm living in this world. So which of these are going to satisfy that? Well, the only ones that satisfy are here, here, and here, which is a third, 3 out of the total 9. So sometimes this is actually can be answered by just looking at this a little bit differently, but there's also some really cool things this tells us about in general probability. There's also, we can still manipulate our formula to actually write that the probability of A and B occur is the probability of B occurs after A is already known times the probability of A, or the probability of A is the probability that they both occur, or the probability that B after A. So we can use all these things to actually figure out the different probabilities we want. And that is the basic concept of Bayesian statistics, which, interesting enough, Bayesian statistics, I'm going to get you, this is going to look very familiar, but I'm going to explain this in just a second. But the first interesting thing that I always love to tell people is, and this is true of actually a lot of mathematicians, Bayes was actually a minister. A lot of mathematicians over the years have been either religious figures, or else they also have been involved in philosophy. This is very, very common because of some things that have been done about stuff. So Bayes, he kind of worked on the sum, and therefore it's named after him. But the probability that B sub K, so we have all these different disjoint events that could happen. The probability that one of them happens given A is probability of A given B. So notice the opposite order times the probability of that specific B, just in general. And then down here, probability of, notice all these products are down here. It's A times the probability of one. So this, interesting enough, this denominator is, if you think about it, it's all the situations, and then I only picked one of the situations up here. But because we're adding all the denominator values, nothing's going to cancel out. It's going to make the bottom guaranteed to be at least one, because it has to at least be probability of A given BK times probability of BK. Has to be somewhere in there, and it should be more. Now, to see this more at play, let's just consider something a little bit along these lines. And that's a medical test. So this is where sometimes we get things kind of weird and people misunderstand statistics. So they can say different things and people misunderstand what that means. So in medical tests, you have two incorrect results: a false positive. That means that something says the patient has a disease when they don't have it. Because a positive test is a test that says that someone has a disease. So false positive, something that says they're sick when they're not, and a false negative, it says they're not sick when they are. So these are both not good scenarios. We can discuss which one is worse. But in general, for healthcare screenings, it's better to have a false positive than to have a false negative. And the reason being for that is if you get a false positive, if you tell someone they're sick and have to run a second test, that's a whole lot better than if you tell someone that they're not sick and they go home very sick and now they're not gonna, sorry, my screen flipped on me. And now they're possibly gonna pass away or something. So let's consider a specific medical test and for a disease that found 5 people out of 1,000. So the probability of the disease is 5 out of every 1,000 people. Okay, that's 0.5%, not 5%, 0.5%. And the rate for a positive false positive is 3%, and the rate for a false negative is 1%. As we can clearly see, false positives have a higher rate than false negatives. That's good. But let's use this information because that means that 99% of the time that a person tests positive. So remember, this false negative rate means would be the rate that they test negative and they don't have the disease, and they test negative and they do have the disease. So the opposite of that, 99%, would be a person who tests positive for it. So if they're sick and they test positive. And 97% of the time is that someone who doesn't have the condition does test negative for it. So these are pretty good numbers. Normally we get pretty excited about them. So let's talk about what's the probability the random person tests positive disease actually has the disease. So what's the likelihood if I take the test that I actually have it? And then our second question is what's the probability the random person tests negative for the test does not in fact have the disease? So the reason we're asking these questions is kind of to understand a little bit more about these questions and see some interesting things. So, because remember, there's actually 4 outcomes. Either someone has a disease and they test negative, they don't have the disease, they test negative, they have the disease, they test negative, they have the disease, they test positive. So there's 4 possible scenarios that we really have in this situation to deal with. So let's consider a person chosen at random from these screened. Let's let A be the event that person tests positive for the disease. And B1's the event the person actually has it. So the probability of that they test positive, given that they have it, is a 0.99. We got that again because the failure rate was false negative was 1%. The probability, the opposite probability was obviously the probability that they test negative and they actually have the disease, and that's 0.01. Similarly, the probability that they don't have the disease and they test negative is 97%. that they have the disease and they test negative. Sorry, that they don't have they have the disease and they test positive. Yeah. So they test positive and they have, given that they do not have the disease. So this is, they test negative and they test positive when they do not have the disease. So B1 is they have the disease. B2 is they don't have the disease. Make sure we're real clear on that. So we now put all these numbers in. So the problem for the part A, we want to know the probability that someone who has a disease actually has a disease, given that they actually tested positive. So that's the probability that they tested positive, given that they had the disease, which is 0.99. And what times the probability that B1 that they have the disease, which remember is 0.05005 or 0.5% over. And now all down here is again, we're going to probabilities that they test positive both for when they have the disease and when they do not have the disease. And we're going to add those two values together. Because the probability that the probability that they don't have the disease is going to be 0.995 because it's the opposite of these values. So these values are going to be opposite, but these aren't necessarily mirrors of each other. If we do that, there's actually a 14.2%. So let's remind what that means. That means that the probability that a person with a positive test has the disease is actually 14.2%. So if I get a positive result, there's only a 14.2% chance that I'm actually going to have the disease if I get a positive result. So, and by the way, I always get mixed up with positive and negatives for tests because I feel like testing positive for a disease should be a negative thing, but it's a positive thing because it's yes or no, and it's Boolean. So it's okay. Here, let's go to the second question, which remember was, what's the probability that someone with a negative test does not have the disease? And in this case, we have we can go again through all the probabilities we can put in because we're dealing with the complement of a negative test and then times the probability that they don't have it on the top. Probability they do have it. And this is going to be really, really small right here. And this one's going to be pretty close to 1. And so as a result, this is 0.99. So let's think about what that really means. That means if you get a negative test, there's a really, really, really strong probability that you actually do not have the disease. Because the likelihood of having a negative test when you don't have the disease is a 99.995%. That's really, really good. But coming back here, if I test positive, that a person who has a positive test actually has the disease is actually only a 14.2%. That means there's a lot of chance that they could test positive and not have the disease. And again, this goes back to just how they want to actually make this work out. So you might be surprised. This is actually how they often design things because again, it's easier to run more tests just to double check. Okay, we think you have this. Well, let's run a couple more tests. Then let's rush you into surgery. And then we find out you actually don't have it and the test was wrong. That's way more costly than in this other situation. And further, their most concern is sending people home who actually have a disease and they're not testing positive. This is very much true. This came up a few years ago when we had COVID. There was a lot of COVID tests and even at home tests. What people misunderstood about many of those is that COVID tests were more likely to show that you tested positive when you didn't have the disease. Again, because it's the same general idea. So they're more likely to say that you tested positive when you didn't have it than to say you tested negative when you did. So despite what everyone felt about tests, this is how usually they're designed based on the probability. All right, so let's move on and let's talk about independent events. So this means we're going to talk about two events that the outcome of the first does not depend on the outcome of the other. So if I'm tossing a coin, I can flip it once. There's 50-50 chance. Flip the second one, it's still 50-50 chance. The reason that that is important is because we do have events that are completely independent. So just because I pulled something out the first time does not change how it happens the second time. So, and this is where people get mixed up. We feel about hot streaks. So if I flip a coin, for instance, and I get 10 heads in a row, as human beings, we often say that we're due or we're likely to have a tail come up. The truth is, the next time I flip the coin, it's just as likely to get the same result. And this is a fallacy, real quickly, before we get into the actual math of it. That is the problem with a lot of people in gambling, is they lose and they feel like they have to be balanced out at some point in time with a winning, or I'm winning and therefore I'm going to start losing at some point in time. Statistically speaking, if you play long enough, yes, your losses and wins should come out to a certain number. That's called the law of large numbers. However, there is no thing that guarantees that. Like when we say large, we're talking like a million situations. So unless I'm flipping a coin, like if I flip a coin a million times and in totality, it's still dramatically skewed in one direction, like it's still like 5% in the direction of tails, that's a problem. But that still doesn't change the likelihood of things. So we're going to talk about random events, and the probability that they're independent is really the probability of A given B is really just probability of A, and probability of B given A is B. Or and doing some quick math, that shows the probability of A and B is the probability of A times the probability of B. So let's look at just a couple quick examples about how this works a little bit. So let's suppose that A and B are events and that they are disjoint. That is what I mean by this fancy symbol right here. So remember, this means that their intersection is zero. Probability of A is not zero, and probability B is not zero. And the probability of A intersect B is not equal to probability of A times probability of B. Well, this is why we have, and by the way, since that's not true, then they're not independent. Well, this is not true because this, if A intersect B is the empty set, then this side is going to have to be zero. And this is going to be, if these are both not zero, then their product is not zero. So that gives me this. And because we know that zero times zero, a non-zero times non-zero is, well, non-zero, then this is not possible. But that in of itself tells us, again, going back to this definition of independent sets, that they are actually not independent. Okay, so that's the key thing to kind of talk about. So let's kind of look at this. So we're going to talk about coin that's loaded, which means heads are going to come up. I just mentioned they're going to be off. Heads are going to come up 0.6 times. The coin is tossed twice. Although the probability is greater than the probability of tails, there's no reason to believe whether the coin lands heads or tails on one toss will affect whether it lands on the second toss. That is a result of being independent. Because, and it actually comes back to this right here. If you have a coin, what's the probability that you have a head and a tail? Well, that's zero, but the probability of a head was 0.6 and the probability of tail was 0.4. So this does not equate, which means they are. So that's why we actually are going to have a problem here in terms of dealing with this stuff. All right, sorry. All right. So let's do a couple problems. Let's talk about what's the probability of obtaining two heads, probability of obtaining one head, no heads, and at least one head. So the probability of obtaining two heads. Well, we have four options: heads, 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 tails, tails, heads, tails, tails. These are not equally likely, by the way, because each toss is completely independent. So we got to look at each situation. So if E is the event that the heads are first, and F is the event that tails in the second toss, that's E and F are 0.6 because we're assuming that they're independent of each other. And so you get the probability of that to be 0.36. So that means that this heads and then tails 0.36. Well, if we'd first, one head can be, so that's the first thing. What's the probability of two heads, which is a head and then a head? And again, if I have one head, can be attained two mutually exclusive ways. So exactly one head, then I have this one and this one. And so we're going to figure out each of those situations. And then we're saying what's the likelihood of each of those situations, which means we're going to add them together because there's no intersection of those two situations, which is 0.6 times 0.4 and 0.4 times 0.6, or 0.48, 48%. Now, again, notice I had 36% here and 48% here. And technically, if we come back to our cases, we've now covered heads, 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 tails, and tails, heads. The tails, tails is the only option left. We could simply say, well, that's going to be 48 plus 36, what's left over, and get the simple number that that is going to be 16%. Just doing the quick, you can also calculate this 0.4 times 0.4. But we can add this up, and that's a key thing going back to another one of the axioms was for the complement, we can take one minus what I do not want, which gets to this question, our last question, which is what's the probability of obtaining at least one head? Well, remember the probability of getting two heads. I could do this probability of one head plus the probability of two heads. We could also do that as one minus the probability of no heads, which is the 0.16. So there's two ways that we can actually get around this by attacking this very methodically and kind of getting it. All right, so let's keep with this coin idea where it's probability of heads is 0.6. If we repeat this how many times, what's the expected value for the number of heads? So in other words, remember we're doing expected value here. So we're going to ask, how many heads should I get if I do this 3 times? So if we're talking about just the coin being tossed twice, we have two possibilities. We have 0 heads, 1 head, or 2 head are my options. The probability of 0 heads was 0.16. The probability of 1 head was 0.48. Probability of 2 heads is 0.36. And so if I multiply that times those situations, I get a 1.2, which really means if I flip the coin twice, there's a really, really good chance that I'm going to get at least 1 head. Generally, I'm going to get at least, I'm going to get 1, maybe even 2. So there's a really good chance we can leverage this and keep playing with this over and over again. Now, this then leads us into more properties of independent. So if I have A, B, and C are now independent pairwise, which means A and B are independent, B and C are independent, and A and C are independent. They don't have anything true. And those would result in the first 3 conditions being true. Then we refer to the 4th condition also has to be true, which is the probability that all 3 events occur is the product of all 3 events. And we can take this a step further by saying, what if I had not just 3 events? What if I have n events? Then the probability is simply multiplying them, the probability of each of those things all together over and over again. All right, so let's go back to our coin to see how this works. Except instead of flipping it twice, we're now going to do it 8 times. Excuse me, we're going to do this 10 times and we want to get 8 heads. So what's the probability of attaining at least 8 heads and what's the probability of obtaining 8 heads? Well, the probability of obtaining 8 heads is literally going to be heads, 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 heads. So what's the probability? But I have to have 2 tails mixed in here. And so one of the ways we think about that is I have 8 heads, so 0.6 to the 8th power and 0.4 squared, because I have to multiply both these. Now we could obviously have moved these around any which way, even if I had different. So this was if I had the probability of head, 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 tail, tail. But I could have done this all the different ways. So really then the question is, this is going to give me a number, but it's going to be incomplete because that's only for the situation where I had all heads and then 2 tails to end, which is interesting enough is the same number as if I had 2 heads, a tail, and then 5 heads, a tail, and then a head. So I got the same number for each of these. So the question really then is, how many ways could I have flipped the coin 10 times and gotten 8 heads or 2 tails? Same question. We could have done it 10 choose 8. So this is again where probability and combinatorics comes back to play. So we're going to 10 choose 8 times this situation, and that is going to be the number of times that I can have 8 heads. Now, again, I'm not, even your book isn't going to multiply this out because this is big and ugly. When we get to doing the next part, which is for 9 heads, it's actually, and 10 heads, it's the same thing. What is the number of ways that we can choose 9 heads out of 10? So it's 9 choose 10 or 10 choose 1. You can choose the tail or choose the heads, your call, times 0.6 to the ninth power times 0.4 because you only have one tail. And then for the 10, this number of ways you can pick 10 heads is 10 choose 10. And then all we have to do is add those together, those three situations. Because if I'm flipping it 10 times, at least eight just means 8, 9, and 10. We're going to want to add those probabilities together. There is no fancy way to just delete everything else. However, if I modify this slightly and I said at most, at least 3, well, then it's easier to count the number of ways to not the 0, 1, and 2 case and subtract those. So you're always trying to figure out which one is easier to approach, which is easier to count, what I want or what I don't want. And that is what we use in probability all the time. So be flexible and be familiar. By the way, you throw all this in and you're going to end up with that out 1.167 or about 16.7%. All right. So last but not least, this little note that you just said where it's n choose k, p to the n minus k, 1 minus p to the k. These actually have a very fancy term if you want to go Google it. It's called binomial probabilities. I'm not going to make you memorize that. It's just kind of fun because they deal with the binomial idea. But again, they're super useful in situations like this where I have two situations that I'm kind of working on and I'm trying to figure out how to do those. It could get messier if I had a multi combination, which is actually even crazier, where I'm like, all right, how many ways are there to do this, 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 and this? And now we got to mess with a lot of different situations. So we generally prefer something and its complement, and then we just work through all those probabilities to get the probability of something happening. Good luck, and let me know what questions you have.